All right, so ladies and gentlemen, this video is about chemical reactions. So we're introducing and we're moving into chemical reactions. We talked about bonding, and now we're going to look at is how it is that these chemical substances interact with each other and form different chemical substances. So in particular, what we're going to be looking at is just kind of an introduction to how do you know when a chemical reaction is occurring. Well, here's the key thing. After a chemical reaction has actually happened, substances are no longer the same. They are completely different. That's what makes it a chemical reaction. So bonds are broken and new bonds are formed. So again, how do you know when a chemical reaction is taking place? Well, there's some indicators. We can have things such as bubbles that occur. We could have the formation of a solid, which is a fancy word for that is called a precipitate. We can have things like color changes that occur, or maybe we can even see the idea of light or feel heat that's being released from a chemical reaction. So how do you show a chemical reaction? Okay, it's what we use is what is called a chemical equation. All right, so in order to describe a chemical reaction, we use symbols in order to make it easier rather than writing out a long sentence or something like that. And it's organized to show the interaction of the substances. So I want you to think of it as almost like a recipe. Like, how are we going to make this particular product that we're interested in? We don't just willy-nilly mix stuff. We try and make it so we're making a particular substance, okay? And it's separated into two parts. And I'm guessing you've heard this from middle school, but you had the idea of the reactants. These are the things that are reacting. And you also had what are called the products, okay? And I'll give you a very simple example of this. This is we got hydrogen reacting with oxygen to form water, okay? And yeah, this happens, all right? And so hydrogen is actually breaking bonds, and so is the oxygen, and when it reforms into water. Okay. Now, there are a ton of different symbols that are used to give more detail about chemical reactions. Kind of like the idea of a recipe, there could be a lot of intricate pieces of information that are given. And some of these symbols can include things like pressure, how much heat is applied. We can look at whether we add a catalyst. Okay, and you're like, catalyst, what's a catalyst? It's something that speeds up a chemical reaction. You probably heard it in your biology class, except you didn't call it a catalyst, you called it an enzyme. Okay? We have the states of matter, whether it be a solid, a liquid, or a gas, and even the idea of the formation of a precipitate or a gas. Okay? So here are some of the symbols. No, you don't have to memorize them all, but there's a couple key ones that I would suggest knowing. For example, the ones that involve the states of matter. S for solid, L for liquid, G for gas, and AQ, which is a fancy term for something that's dissolved in water. The other one that I think is super important is on the right-hand side there, which we have an arrow going in one direction saying that it produces or yields, indicating a chemical reaction. We can even have chemical reactions that are reversible, and as we get further down the road, we'll look at those, okay? So, but the thing is, we need to be able to interpret chemical reactions. What is it saying to us, all right? So, chemical equations, they can be translated into a sentence or vice versa. We can take it into a sentence and put it into a chemical equation. I'm not going to have you do that, but I do need you to be able to recognize that when you're given something like this, such as hydrogen reacting with oxygen to form water, that we can specifically point out what they are in the sense of two dihydrogen molecules react with one dioxygen molecule to form two molecules of water. Why am I saying molecules? Well, because that is the smallest component. They're bonded covalently, and so therefore they are considered to be molecules. So that is something that you do need to know, is being able to know if it's a molecule or an ionic compound and what it would be called. So it depends on the types of bonds in the compound, all right? So if atoms are held together by covalent bonds, we call it a molecule. On the other hand, if it's ions that are held together by ionic bonds, then we call it a formula unit. Okay? It's the smallest component of an ionic compound is called a formula unit. Right? These two terms are going to come into huge play as we move further on down the road. So make sure you commit those to memory. Okay? So let's talk about what we're going to be focusing a little bit of our attention on today, which is the idea of balancing chemical equations. Okay, so if you look at the equation that I've been using as an example, we have 2H2 with G standing for gas plus O2 with G standing for gas, forming 2H2O Okay. Now, the numbers in the front of the compounds allow us to balance the equation, meaning, here's the thing. In order for a chemical reaction to occur, it must obey the law of conservation of mass, meaning that mass cannot be created nor can it be destroyed. Okay? So we use coefficients, the numbers in the front, in order to make it so that the reactants and the products are equal on both sides. So as with a recipe, you need to know how much of each ingredient you need to determine how much of the product you will make. Okay? So knowing this, I need 2 parts hydrogen, 1 part oxygen to make 2 waters. Okay? So the key is, folks, when we have something like this, to balance an equation, we want to make it so that the reactants are equal to the products. Okay? The reactants are equal to the products. Remember, the reactants are on the left-hand side of the arrow. The products are on the right-hand side of the arrow. So what you can actually think of as you go through this chemical equation is you can actually think of the arrow as meaning an equal sign. Okay? An equal sign. So what I'd like to do is I'd like to go over how it is that we can balance an equation. Okay, so here's the equation that we're going to work, and I'm going to show you how to do this, my mental thinking as I go through this process. Okay, so I'll be writing on the screen here in just a second. So we're going to try one together. I've got aluminum, and it's reacting with oxygen to form a substance called aluminum oxide. Okay, aluminum's a metal, oxygen is a nonmetal. So I know that when I take a metal, which has a very low electronegativity, and I have a nonmetal, which has a very high electronegativity, the oxygen is literally going to steal the electrons from the aluminum, forming an ionic compound. And that's what we have here. So again, I want you to think of that arrow as an equal sign. Okay, so we need to make both sides to be equal to each other. So in order to make it easier, I've actually developed this little spot where literally I'm putting lines in front of each one of the substances to make it so that I can show you the coefficients that we're going to put in the front. So I'm going to adjust my screen here, all right, and I'm going to get myself a pen so that I can do this. So here's my logic behind it. I want to make it so the left-hand side, the reactants, are equal to the products, okay? Now remember, these on this side, this is the reactants, okay? Over here, these are the products. And again, they need to be equal. Why? To obey the law of conservation of mass, okay? So I make this real simple. I like to start, okay, on the left-hand side with the first element. So if you look there, I have aluminum, okay? And I only have 1 aluminum here. There's only 1 of them. But on the right-hand side, I have a total of 2. So I'm hoping that you all agree that in order to balance out the aluminums, I would need to put a 2 right here. So right now, my aluminums are balanced. However, let's take a look at our oxygens now. Over here on this side of the equation, I have 2. But over here on this side of the equation, with the products, I have 3. Now, if we have 2 and 3, those numbers don't go into each other very easily. But what is the common multiple between the numbers of 2 and 3? The common multiple of these two numbers would be 6. That's the common multiple. So what that means is I need to make it so on the left-hand side, on the reactant side, I need to have 6 oxygen. And on the right-hand side, I need to have 6 oxygen. So what number times 2 will get me 6? I'm hoping that you recognize that that would be 3. And what number times 3 would get me 6? And I'm hoping you recognize that that would be a 2. Now, I hope you recognize another important thing. I keep saying that, recognize, recognize, recognize. I did not change any of the tiny little numbers, what we call sub subscripts. Okay, this is a subscript. Ooh, there we go. I'm not changing those. I'm not allowed to change those. That'd be like changing the ingredient. We can't change the ingredients. The ingredients need to be the same. Okay, I can only change the amount of each of ingredient. Okay, so if we look at this and we examine this on our screen that's in front of you, I've caused myself a problem. When I balanced the oxygens, I actually made it so the aluminums are no longer balanced. Take a look. Over here on this side, I have a total of, well, hold on, let me get my little pointer. Okay, I have 2 aluminums. But over here now, look, I have 2, but times 2. What's 2 times 2? 4. I have 4 aluminums. So I need to actually make a change to my value. I need to change this 2. And this 2 needs to change to be a value of 4 instead. Now I have a balanced equation. I have 4 aluminums on the reactant side. I now have 4 aluminums on the product side. I have 6 oxygen on the reactant side, and I have 6 oxygen on the product side. So it is a little bit of trial and error as you go through this. Okay, so it's going to take a little time to do it. So let's try another one. Okay, in this one, we're going to look at methane. And methane is reacting with oxygen to form carbon dioxide and water, right? And again, I want you to think of the arrow as an equal sign. So let's go ahead and put our lines in the front so that we can adjust this, so that we can balance it out, all right? So looking at this, okay, let's start with the easy stuff. Now, I will tell you right now, here's the hardest part. Take a look at these 2 substances over here. Look at the carbon dioxide and the water. You notice that we have oxygen in this compound and oxygen in this compound. Here's the problem. That's going to be an issue. That's going to make it to be a painstaking process. So what I call those split elements. We're going to not do them until the very end. The very end, okay? So take a look. Start simple. Look over here at the carbon. How many carbons do I have here? 1. How many carbons on the other side? 1. My carbons are already balanced. Sweet. Okay. Now we take a look. All right. Carbons are balanced. Let's look at hydrogen. I have a total of 4 hydrogen here on the reactant side. Let's take a look at the hydrogen on the other side. I have 2 hydrogen on the other side. So I'm guessing if I put a 2 here, that now my hydrogens are balanced. And 2 times 2 is, yeah, you got it, 4. Okay? So my carbons and my hydrogen are balanced. What's the only thing left? You got it, oxygen. So we're going to look over here on the other side. So I've got how many oxygen here? 2, plus another 2. Because 2 times 1 is 2. And 2 plus 2 is, last time I checked, there would be 4 oxygen on this side. And over here on this side, right now I only have 2 oxygen. So if I put a 2 in the front here, I now have a balanced equation. And you're going to say, but we didn't put anything here. Do I have to put anything special here? No, you could put a 1 there if you wanted to, but it's not required. I hope this helps you balance some equations here, right?